Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today as it is every day here in my virtual classroom. Step one aside as we dive into a section 11.1 to 11.3 quiz in the Big Ideas Math Integrated Math 2 textbook. This is the beginning of chapter 11 where we deal with things on circumference, areas, and later volume, but right now circumference and areas, specifically circumference of circles and arc length of circles, areas of circles and areas of sectors, and then areas of polygons. We've done kites, rhombuses, and regular polygons. That's the 11.1 to 11.3 material. 12 questions in this little review basis here. Not very many, but I hope it covers at least everything in one fell swoop for you guys for this review, for whatever you quiz from your classes. Or maybe this is a quiz that your teacher gives you for classes, in which case this is a solution guide video. So check out the description section down below and download the PDF if you'd like to for this single page item, and follow the timestamps for each individual problem that is provided for you as well. And also please give me feedback here. I'm going to jump into this right now and get us started. Let me know if whatever you're watching this on, computer, laptop, phone, tablet, what have you, if this is legible for you. I just did get feedback lately on the chapter review portions, or the things like this where they are full page items and not kind of split in half, where I have to zoom out a little more to fit it so I can still write on this side, and that it's less legible. My first recommendation, of course, my few things for you if you have trouble still, is make sure that you are in full 1080p resolution so that it's most legible. I hope that everything that I'm saying is very clear, and if I copy paste items I do, and that you do download that PDF thing as well, or print it out, or you have it handy for yourself. I don't know if most people who watch this are just getting review outside of this actual stuff, like I'm just here to review, or if people are saying like I actually have this homework. So either or, let me know if I zoomed in enough for this one. Otherwise I am going to seek other alternatives, like the way that I lay things out possibly, but just please let me know. All right, thank you, and without further ado, let's dive into this and let's start. Numbers 1 through 3, we are going to find the indicated measure. These are out of section 11.1, which is most likely something to do with circumference and arc lengths. So in the very first question, we're going to find the measure of arc EF. Now EF is this guy right here. It also would represent the central angle. And the arc length, or the arc measure, or the central angle, is a certain amount out of 360 degrees. So to find this measure of arc EF, let's set up a proportion where this is out of 360 degrees, the same way as that arc length you see, that 13.7 meters, is out of the circumference of the entire circle. So this 13.7 out of whatever the circumference is the same fraction as that arc measure we're trying to find. Now the circumference of the entire circle is found using 2 pi r. 2 pi times your radius, and in this case your radius is 7 meters. So we have something kind of set up for us to solve for the measure of this arc given that proportion. Let's keep moving forward on that simplification of that guy. This, I can multiply both sides by 360, and I'll have 13.7 over 14 pi, multiplying that by 360, and this is one of those cases where you're just going to let your calculator kind of do some work for you. During this section, we were rounding a lot to the nearest hundredth, 2 decimal places, so I'll continue doing that. And in the calculator, I'm going to be typing this. I'm going to do 13.7 over 14 pi. However, I have to make sure that in 14 pi, at least for my calculator, I use parentheses, so pi remains in the denominator and is not multiplied by the numerator of 13.7. Now this times 360, for example, see, that's going to be in the numerator. This is going to be in the denominator together. So this will give me my value of 112.14 about. Now this is in degrees, 112.14 degrees. This is how many degrees out of 360 that arc length is taking up on the problem. Let's jump to number 2. On number 2, now we're going to find the arc length based on the central angle. So using the same proportion idea, let's have the setup of this, and we still have to find circumference and all that. So now the measure of arc QS is the same as that central angle QRS. It'll be 83 degrees. Whatever 83 is out of 360, and it's unlikely that can reduce, the arc length we're trying to find, QS, I'll just call it an X, because if I said QS, then that would kind of be a chord. So this X would be out of 2 pi r. 2 pi times your radius this time is 8 pi, because your radius is 4 centimeters. So this answer is going to be in centimeters. It's going to be some certain length. How long is QS based on the entire circumference being 8 pi? It's the same fraction here. If you multiply both sides by 8 pi, you'll get x equals 83 over 360 times 8 pi. It's literally that fraction of 8 pi that you're taking. And we will be rounding this answer, so this time I'll just kind of type it out here on the side. You won't see it. 8 pi over 360. Oh, 83 over 360 times 8 pi. And I'm getting 5.79 about, and this is going to be in centimeters. And there you have it. Now, does the answer make sense to me? I guess 8 pi is probably around 25 centimeters. This is probably like a little more than a fifth of it, and that's a little more than a fifth of 360. So I feel it. It's working out. If I had something like 20 centimeters, I'd say something went pretty wrong. Number 3, we're going to find the circumference of circle N. Nothing is changing with regard to what we have circumstantially, a proportion we can set up and use to solve. So 48 over 360, and although that can reduce as a fraction, we're going to use the calculator anyway to get our stuff, so we're good. Equals our arc length. This time, oh, by the way, X is the, for this one, this is the arc length of QS. Our arc length this time is 8 inches, and now we need to find the circumference. Now, circumference may be 2 pi r, but they're just asking for the circumference, not the formula to get the radius. So I just need C in this case. So as far as this goes, if I, let's do this. If I multiply both sides by C, I can get, because I got to solve for C. So if I multiply both sides by C, I'll be getting it out of its own denominator there. And then if I multiply both sides by the reciprocal, 360 over 48, like that, that'll get these to go away here, which means this will be times 360 over 48 here, which that's what I'm calculating. C, the circumference, will be 8 times 360 divided by 48. Now, I don't need a calculator for this. 8 over 48 is 1/6. 1/6 of 360 is 60. So your circumference in this case is 60 inches. It's exactly 60 inches. This is the 2 pi r aspect of it, which means the radius of this problem technically would be some sort of irrational value because I got to divide by 2 pi to figure it out, but we're not trying to figure it out. That'll be number 3. All right, numbers 4 and 5, we're going to convert the angle measure. We're going to convert 26 degrees to radians and 5 pi ninths radians to degrees. Now, the deeper you get into this when you take future trig stuff, when unit circles, you take integrated math 3, whatever kind of class it's in, you're going to learn one very big basic notion is that pi radians is the same as 180 degrees. Pi equals 180 is our way of saying that. It's like a conversion thing. Hello is hola. Hello in English is hola in Spanish. Whatever. 12 inches is 1 foot. That kind of thing. So there's a conversion to that. And you can multiply by a ratio to do that or literally turn pi into 180 or 180 into pi. So when we convert 26 degrees to radians, I'm going to take 26 degrees and multiply this by pi over 180. This is a way of, the way that I do it is almost the same way that you're seeing in this proportion stuff. Remember when we took 83 3/60ths of 8 pi? Here I'm going to be taking 26 1/80ths of pi. This is what your answer will be in terms of pi. The thing is, though, you want to reduce your fraction. So if I divide these both by 2, I get 13 pi over 90, and I can't see me be able to reduce that any more than that. But that's the answer. I know a lot of people say, oh, do you multiply by this, by that? If you forget, just think about what fraction of 180 you're taking, and that's how many pi. Because pi is 180. So anything in proportion, pi over 2 is 180 over 2. It's 90. And that's just how all this stuff works. That's number 4. Number 5 is probably even easier with that in mind. If pi is 180, there's a pi there, so I will replace it with 180. So if 5 pi over 9 radians equals 5 times 180 degrees over 9. Now, if you don't know what 5 times 180 is, 900 by the way, you can do 180 over 9 first, make it smaller. I'd always recommend that. 180 over 9 is 20, and do 5 times 20, which is 100 degrees. And if that didn't, if you wanted to do the 5 times 180 aspect that I was just bringing up, I was just mentioning there, 5 times 180 is 900, and 900 divided by 9 is still, yet again, 100. All right, that's numbers 4 and 5. Let's look at numbers 6 and 7, where we find the area of the red sector and the blue sector. Interesting, when I did this section at the time, this is 11.2, by the way, I called it salmon the entire time. I said, on my screen, it doesn't look red or orange or pink. It looks salmon. They actually call it red. So area of red sector, let's copy paste this image because maybe it's too small for you, but either way I might want to manipulate this a little bit. The red and the blue are very related. Whatever's not red is blue for the area of the entire circle. And the area of a sector is a fraction of the area of the circle, the same way that an arc length is a fraction of the circumference of your circle, like that. So we're going to do the same thing here for the area of the red sector. Area of red sector. Now I am going to just call it X when I set this thing up. 100 degrees is your central angle. That's also the measure of arc HK. So whatever 100 it is, whatever 100 is out of 360, our area of our red sector will be out of the area of the entire circle. Now a circle's area is pi r squared. So pi times 12 squared will get us there, as 12 is our radius. Let's clean this up a little bit just because we can. If I divide everything by, I guess, 20, I get 5 over 18 here. I just want to make something smaller because I'm able to. And this is 144 pi. I'm even inclined to give you more of an exact answer first before the approximated, just to have it. This 5/18 will also actually help me for this other part. Well, either or. But if I multiply both sides by 144, I'll get 5. We're taking 5/18 of 144 pi. And as I said, if you wanted to go more exact before you go to the calculator, you could work on fraction reduction, multiply the stuff. I'm kind of inclined to right now. 144 might divide by 18. I think it does. I think it's 8. So this is 8, and 8 times 5 is 40. I think this answer is 40 pi. 40 pi square yards. Remember, this is area, so we have square yards. That's an exact. That's an exact, but we are going to go ahead and approximate it. And 40 pi square yards is, and I'm trusting my own internal math with that's right, but this is 125.66 square yards, like that. I think, I hope, I wish, so that way you don't get anything actually wrong. So with that in mind, I just lost my page now that I went to the calculator. With that in mind, we are going to find the area of the blue sector next on number 7, and there are multiple ways you can go about it. They all get to the same result. You are using this central angle now, which would be 260 degrees, as 360 minus 100 gives you the 260. So it's the same idea of proportion. Whatever 260 out of 360 is, your new, if I called it Y, your area of this blue sector would be out of your area of your entire circle. So what I can do instead, remember, as the fraction reduces, I stated whatever is not red is blue. So whatever is not 5/18 out of 1 is the other part. So I can subtract 5/18 and get 13/18. Y is going to be 13/18 of 144 pi in that case. So I can go straight into that without having to set all that stuff up. I already have the reduced fraction. Makes it pretty easy to look through, especially when it comes to me getting an exact answer. 144 pi over 18 is 8 pi. Yeah, that's right. Okay. 8 pi times 13 is 104 pi square yards. So that's an exact answer. So let's do 104 pi in the calculator. 104 pi. And I'm getting 326.73 about. 326.73 square yards. And those are the two answers that we're likely looking for there. So it depends on what you want to do with that stuff. There's some shortcuts to be had, obviously, as I'm speaking a little bit longer on it. Maybe it's not so much a shortcut to you anymore. But in the long term, it can. We're about making sense of these problems, not just solving them, at least for the most part. Okay, numbers 8 through 10. Numbers 8 through 10, we have a regular octagon inscribed in circle C. This is section 11.3 material on areas of regular polygons and things like that. So we have a regular octagon inscribed inside there. Regular means all sides and angles congruent, which means we build a lot of isosceles triangles here. But there are certain words that we have brand new to here, and that's what number 8's all about. Identify the center. The center of, it's not just of the circle, it's also the regular octagon. The center is C. Now it says a radius. Whenever they say a radius, an apothem, and a central angle, they're not asking for the measures. They're asking for labeling one of these things. So a radius, there are two that I see that are actually shown. CR is an example of a radius. That's a segment from C to R. It's also the radius of that circle. That's a good reason why they have that name. And also CY. I'm giving you both of them in case you're like, wait, I put CY, you said CR. I don't know if I'm right or not. Apothem. Apothem. So a radius is the longest distance from center to a point on your regular polygon, and the apothem is the shortest distance from point to center to point on regular polygon. So the one here longest is to a vertex, and the shortest one is the perpendicular one. The apothem is the C to Z, Z being a point on the octagon, not on the circle. It's not a radius. CZ, the only one that's drawn for us, is an apothem of the circle. Here would be another one going from C straight down to here. If I called this like Q or something like that, that would be another one. Another one. A central angle. Central angle is an angle made by two consecutive radii in your, specifically those ones, two consecutive radii in your regular polygon. So angle RCY is a central angle here. Now, it's important to note that it's specifically only one of those by two consecutive radii because, so RCY, or YCR, it's the same thing. Because to find a central angle measure, you divide 360 degrees by the number of sides, or radii, that your, or angles that your regular polygon has. So in an octagon, 360 divided by 8 would give you it. And it looks like we might have to come up with that on number 9. So number 9, we're going to find the measure of angle RCY, RCZ, and ZRC. See, RCY is the first one we're going to find, central angle. And you're wondering, possibly, how do we find any measures if they don't give us any numbers? I just mentioned central angles add up to 360. So measure of angle RCY, we're going to take 360 and divide by 8 for this regular octagon, and that's 45 degrees. So that central angle that I marked in black right there, that's a 45-degree angle. Now, what we're often going to do in problems where we have to find area with this kind of information is find half the central angle. When the apothem is drawn, it bisects the central angle into two congruent parts. So, to find the measure of angle RCZ, one of those ones that's bisected, you take your 45 and divide it by 2, and you get 22.5 degrees. This is often used because we need to use trig or special right triangles to find a missing value, like the apothem length or part of a side length. When you want to find the area of a regular polygon, those two bits are super crucial for us to be able to find its area. And they're asking for area on number 10, so I'm going to talk to you more about it then. Measure of angle ZRC is not one I've been using as much or at all in the section stuff in the past. I suppose I would have if we talked more about interior angles of regular polygons, but that's been used more for something like IM1 and not as much for IM2, I believe. So measure of angle ZRC, however, because it is a right triangle that you're talking about with that ZRC, Z is the right angle, C is 22.5, so this is the complement of that 22.5, and that's 67.5 degrees on the ZRC. Number 10, the radius of the circle is 8 units. Find the area of the octagon. I'm going to just redraw this octagon as a whole, and honestly, imagine this. So there's no circle around it in our imagination here. Imagine that we're just looking at the bottom portion of the octagon. You see me do this a lot in this section, in the lecture portions, right? There's still this part of the octagon, but I'm not drawing it. All I'm really concerned about right now is just where's my center at C, like that. There's an apothem that I'm going to be working off of. There's this radius that we have a value for, and we're going to get everything else. So this is 8 units of a radius. Now, here's what we're going to do. The formula for the area of a regular polygon, any regular polygon, is 1/2 apothem times perimeter. Apothem is this A right here. We need to find it. In order for us to find it, we'll use that 22.5 degree angle measure that was here, 22.5 degrees, and we're going to use trig to find A. I'm not going to round the value yet. I'm going to round my final answer. So as far as trig-based information goes, the apothem is the adjacent leg to 22.5, and 8 is the hypotenuse. My setup would be the cosine of 22.5 degrees equals a over 8. Multiply both sides by 8. You get a equals 8 times cosine of 22.5. Okay. We also have to find the perimeter of the entire octagon. Now, the perimeter, every side is congruent. And so there are 8 sides. If I find one of the side lengths, I can multiply by 8, and I'll find said perimeter. However, in order to find it, I first want to find one of these mini side lengths, this portion of this right triangle. And because these two are congruent, since the apothem bisects this portion, I will double it. So I'm going to call this little guy x. That's what I've been doing most often here. So this x, or for you, would be like that, like zy on the diagram. So x is found, again, using trig. I can use sine. If sine of 22.5 is x over 8, then multiply both sides by 8. X is 8 times the sine of 22.5 degrees. That also means that 2x, if you double that, that's a side length right there. That's 2x. 2x is 16 times the sine of 22.5 degrees. And the perimeter therefore would be 8 times that amount. So 8 times 16 is 128. So 128 times the sine of 22.5 degrees. Again, multiply by 8 times 8. Okay, so I have my apothem here. I have my perimeter here. I'm going to use them in this formula here and come up with my final area. So the area of the regular polygon is 1/2 apothem times perimeter. And we'll use our calculator to get a rounded value. It was in section 11.3 where we started rounding to the nearest tenth for some reason. I think I was following the textbook in saying that, but I don't know if that's going to be totally accurate. If I were to write an exact answer first, however, 1/2 of 8 is 4, and 4 times 128 is 512. So we get 512 times the sine, I like to write sine first, sine of 22.5 degrees times the cosine of 22.5 degrees. That's an exact answer. They didn't mention any actual units. They just said 8 units. So this would be in square units as an exact. If I use the calculator, make sure your calculator is in degrees, by the way, when you're doing this, not in radians. Let me check mine. Mine's in degrees. So I'm going to do 512 times the sine of 22.5 degrees times the cosine of 22.5 degrees. And I'm getting 181.019. So 181.0 square units. And that's my final result. So yeah, with these, you might say, is there a faster way to do this problem? Not really. The trig is what we need to find these values and such. Not really, no. I mean, I was spending time trying to get an exact looking answer here first. I'm always big on that, especially when typing in the calculator or if it's asked for later, not rounding early. But outside of that, no, that's the way you do the problem. Maybe my layout was a little more, was a little different, but that's still it. Okay. Number 11 is a different setup. The two white congruent circles just fit into the blue circle. What is the area of the blue region? So basically there's a point of tangency here with this circle and a point of tangency here with this circle when they say they just fit in. So what we're going to do is take the blue circle's area, the area of what would have been a whole blue circle, and take out the area of these two white circles here. In order to know how that's going to work, you can see the area of a white circle can be found using pi r squared with its radius being 3. So the area of a white circle is pi times 3 squared, which is 9 pi square meters. Again, don't round early on there. I want to kind of get that a little farther out. Square meters. The area of the blue circle is based on that 3, though. That 3 can be rotated, say, let me put it on the bottom one. This can be 3 here, and then this can be another 3 here, making basically the diameter of the white circle. And the diameter of a white circle, since they're both congruent, means it goes all the way to the center of the blue circle, which means the blue circle has a radius of the white's diameter. It's 6 meters. So the blue's radius is 6 meters. The area of the blue circle will be pi times 6 squared. And you'd be mistaken if you believed that just because you double the radius means you double the area. No, you actually quadruple the area. 6 squared is 36 pi square meters. But the area of this shaded region, what do they call it? The blue region. What do I always say shaded? The area of the shaded region takes the area of the blue circle minus 2 areas of the white circle. So we're going to be doing 36 pi minus 2 times 9 pi, or 36 pi minus 18 pi, which is 18 pi square meters. That's an exact. Rounded, we'll get probably 56 or something like that. 18 pi. 56.548. This is in section 11.2, so I'm going to go to the nearest hundredth again. So 56.55 square meters. Yeah, removing the white ones is all that's left inside the blue with that. Now, there were questions where they asked things about probability. If they asked the probability of this region, you would actually divide this all by 36 pi, obviously not the rounded value, but divide by the entirety of the blue to say what that decimal is. You can write it as a percentage, like, oh, it's about 52% of the entire thing. I don't know, just depends on the section. All right, last question is number 12. On number 12, we are going to find the area of each rhombus tile and find the area of the pattern. Oh, I see. The pattern is made up of those tiles. I was like, all right. So we're going to have to count how many of each thing there is and then multiply by those things. So a rhombus area is, let me pull up a rhombus shape. Rhombuses have all sides congruent, and when drawn in this nature, the vertical and horizontal lines, these are actually diagonals of the rhombus, and diagonals are perpendicular bisectors of each other. The perpendicular aspect also helps us come up with a formula here. If your if your diagonals were called D1 and D2, you take 1/2 D1 times D2. As D1 would be this entire length, D2 is this entire length, the area of what would be a rectangle. This takes up half that space. This is the same for area of a kite, because kites also have perpendicular diagonals. But, yeah, we'll just go on from there. So for number 12, the area of the yellow rhombus is going to be half of D1 times D2. We can do like 15.7 times 11.4. Now, this should be some form of exact answer. There's no rounding to be had. Please make sure that you're writing whatever's exact here. So 1/2 of 15.7 times 11.4. I'm getting 89.49. So this is 89.49 exactly. Square millimeters. That's the yellow tile, rhombus tile. And then the area of the red rhombus tile is 1/2 of 6 times 18.5. 3 times 18.5 would be 55.5, I think. 55.5 square millimeters. Let me double check that. Yes. So 55.5 square millimeters. So the area of this is the last part, the area of the pattern, there are a certain number of yellows and a certain number of reds. I'm going to multiply that by area of yellow plus that number times area of red. Let's count them out because I actually don't know. The yellow, this is going to be hard to not mess up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. And unfortunately for the red, I can't say, so 32, right? Unfortunately for the red, I can't say, oh, there are 50 ones total, so you just subtract. Actually, I have to count those ones out as well. So it's that number. And then for red, there are 1, 2, 3, 4, 5, 6, 7, 13, 14, 15, 16. I'm actually glad I'm marking these. 17, 18, 19, 20, 21. Did I miss any? I think I got them all. So there are 21 of the red ones. So total there are 53, right? There's no real pattern. I'm making sure, yeah. There's no real pattern to the pattern, if that makes sense. Like as far as a counting measure, it just is what it is. Unless it's like some Fibonacci sequence. So this is going to be 32 times 89.49 plus 21 times 55.5. So calculator work will get us the rest of the way. 32 times 89.49. So again, good thing we didn't round early. Plus 21 times 55.5. And this gives us 4,029.18. This is exact. Area of pattern is 4029.18 square millimeters. If they asked us for like square centimeters or something like that, then I suppose that we could come up with that as well. But that should be it. Okay. And guys, that ought to do it for this one. This is Mr. Robinson. Thanks so much for watching. That covered things pretty well, I'd say. It missed on the probability aspect. It didn't find the area of a kite. And never really gave you a diameter for something to then find the circumference or something like that. So, you know, a radius is half the diameter. I mean, it gave us in one of the problems with the shaded region that we use the diameter with a radius. But hopefully that covered things extensively. If not, check out my 11.1 to 11.3 stuff as individual sections to find those problem sets and what else you want to find. Outside of this, guys, moving forward, we actually go to three-dimensional aspects in volume and surface area of prisms, cylinders, pyramids, cones, spheres, all those kinds of things, even probably some certain composite solids, and get ready for those. So guys, take care. Thank you. I will see you in the next one.